Okay. Question number 11. We're going to use the integral test. Okay, here's the pencil. Now, here's our AN. So what we know is AN is 1 over n squared minus 4n plus 5. So your function f of x is 1 over x squared minus 4x plus 5. Now, take a look. This should be decreasing terms. So you want your terms to be decreasing and positive. So take a look at Desmos now. 1 over x squared minus 4x plus 5. Now, you may say, hey, this is not decreasing completely over the interval from 1 to, I should say, infinity. So that what we can do is notice that f is decreasing starting at the value 2 to infinity here. Okay, so these are the x values starting at 2, going to infinity. Then you have a function that's decreasing. So really, you're looking at this sequence this way. Look at the first term. 1 squared minus 4 times 1 plus 5 plus start at 2 to infinity. 1 over n squared minus 4n plus 5. Now, this number here should be 1/2. So what we're really going to apply now is the integral test, really starting at 2, and then all the terms are positive. So we're going to apply the integral test now. Because notice that first term is really the constant value 1/2. So if the sum is finite, 1/2 plus a finite number will be a finite number. But 1/2 plus infinity will be infinity. So we're really going to start at 2 is what I'm saying here for the integral test. All right. So now let's work with this. We're going to integrate from 2 to infinity. 1 over x squared minus 4x plus 5 dx. This is our improper integral, which will be the limit as t goes to infinity. 2 to t, 1 over x squared minus 4x plus 5. So I'm writing at an angle here at home, not very good. So let's try to do a little better here. X squared minus 4x plus 5. So this is going to be our integral now, I of t, that we're going to try to integrate. All right. I of t. 2 to t, 1 over x squared minus 4x plus 5 dx. So in this denominator, let's take a look. because we can probably use, or I shouldn't say probably, we may be able to use partial fraction decomposition here. So can we use PFD? Well, it depends on whether we can factor this denominator. And ladies and gentlemen, I don't believe that denominator is actually factorable. We can put -1 times -5, but that middle term now is going to be minus 6x, not 4x. So this is not factorable. So we cannot use partial fraction decomposition. What we'll have to use now is we're going to have to take this x squared minus 4x plus 5. We're going to have to complete the square here. Okay, we're going to complete the square for that denominator. So the first step, we say, okay, -4/2 is -2. Take the -2 and square it. You get +4. So the third step is going to take this x squared minus 4x plus 4 minus 4 plus 5. Okay, we're actually using this 4. We're adding it and we're subtracting it. So if you guys remember partial fraction, or I should say complete the square here. Now we're going to say x minus 2 squared. And this portion we're just going to add. So we're going to get 1 here. -4 plus 5 would be +1. Okay. So here's what the integral will really be. From 2 to t, 1 over x minus 2 squared plus 1 dx. All right. So now we're going to use a u sub. Where our u is x minus 2, which means du becomes dx. So here's our u here. We replace this with u. So our integral, I'm just going to write down the integral. 1 over u squared plus 1 du. All right. This is inverse tangent u, where u is x minus 2. So we get inverse tangent of x minus 2. We evaluate this from 1 to t. So this is from 1 to t. We didn't have to put those there yet, but we get inverse tangent t minus 2 and oops, let me go back here. I apologize. That's from 2 to t. Okay, remember this is 2 to t minus inverse tangent 2 minus 2, which is 0, and inverse tangent of 0 is 0 here. So, okay, we got inverse tangent t minus 2. This is the I of t with our improper integral right in here. Okay. Inverse tangent of t minus 2. So we're going to take this limit now as t goes to infinity. Inverse tangent t minus 2. So here's what we say. As t goes to infinity, t minus 2 goes to infinity. inverse tangent t minus 2 goes to pi over 2. Okay. And that is a finite value, which means our improper integral converges. Okay, this improper integral equals pi over 2 here. More importantly, the improper integral converges here, which means this particular series converges by the integral test. Okay, I'll write down the word converges. And we just write this symbolically as less than infinity here. So, okay. So this is how we handle question 11 by the integral test. All right. So if I go back to this term here, remember this term is finite, by the way. Al for finite. We don't know the sum of this. We just know it's finite. So just to go back and reiterate, any finite number plus another finite number is finite, hence convergence. Now there's Al plus 1/2, whatever that value is. It's a finite number here. Okay, so this is going over every detail for number 11. I forgot to mention that. So as long as we got that function decreasing, okay, over the interval 2 to infinity, looking at Desmos, this is good enough. Okay, so starting at 2 to infinity, we actually are decreasing. All right, that's a requirement of the integral test. Okay, let's take a look. The natural log of n over n squared now for number 12. There we go. All right. This is the same situation as the last example. Take a look at 1. Okay, we're at 0, and then it decreases starting at 2 forever, and all the terms are positive, right? So this is just like the last example. So you say, well, what am I going to do? I'm going to write this here. This series we have to say the first term, if n is 1, we get the natural log of 1 over 1 squared plus, now the series starting at 2 is going to be a decreasing series. So ln1 is 0, by the way. This numerator is 0. 0 divided by 1 is also 0. So we're just going to look at the series here and try to find convergence or divergence. So an is natural log of n over n squared, which means your function is natural log of x over x squared. We're going to have to look at the integral from 2 to infinity, natural log x over x squared dx, which is the limit as t goes to infinity, 2 to t, natural log x, x squared dx. All right. This is my I of t. We have to find what that integral is. Okay. Now, how to integrate here? We're going to use integration by parts, IBP. Okay. I'm going to let U be, for integration by parts, the natural log of x, and dvb 1 over x squared dx, because we're looking at this as a product here, okay? Natural log x times 1 over x squared dx. All right, let's see if this helps us out. Du dx is 1 over x dx. I mean, I can do the du dx, which means du is 1 over x dx. V is the integral of x to the minus 2 dx, which is negative 1 over x. Let's do every detail. It's negative x to the minus 1 over minus 1. Which is negative 1 over x. Now, integration by parts. uv minus integral v du. All right, what does this give us? We get negative 1 over x natural log x minus negative 1 over x times 1 over x dx, which is negative 1 over x natural log x plus the integral of 1 over x squared dx. So this integral now here is x to the minus 2 dx, which will give us negative x to the minus 1, or negative 1 over x. So we get negative 1 over x natural log x minus 1 over x from 2 to t. All right. Minus 1 over t natural log t minus 1 over t, which will be minus a negative 1/2 natural log 2 minus 1/2. All together, let's write this down. Negative natural log t over t minus 1 over t plus 1/2 natural log 2 plus 1/2. This is I of t now. Okay. We're going to have to take the limit as t goes to infinity of minus natural log t over t minus 1 over t plus 1/2 natural log 2 plus 1/2. So by properties of limits now, we're going to get the following question. Limit as t goes to infinity, negative natural log t over t minus the limit t goes to infinity 1 over t plus the limit of the constant 1/2 natural log 2 plus 1/2. What we know, this goes to 0, And the limit of a constant is a constant. So the question we're really going to have now is, what is this going to be? If I apply my limit and I keep the negative sign as a numerator, we get negative infinity over infinity here. And that's an indeterminate quotient. We're going to use L'Hopital's rule for this limit here. So by L'Hopital's rule, now we get the limit t goes to infinity of minus 1 over t over 1. This is by L'Hopital's rule, which will be the limit t goes to infinity of minus 1 over t, and then this goes to 0. So, ladies and gentlemen, it looks like here the limit of that I of t, I won't write it down, is 1/2 natural log 2 plus 1/2, which is actually a finite value. This whole thing is finite. Okay, so we have convergence of the improper integral. Convergence, this is finite. So what that'll mean simply is that this series converges by the integral test. Okay, you got convergence here. This sum is actually finite. Okay, so we'll just say, hey, you're finite, and that just means you have convergence. Okay. All right, the series here of 1 to infinity of n over n to the fourth plus 1. And we can see this is going to be strictly decreasing series from the interval 1 to infinity. So just looking at the graph, we know that it's decreasing here from 1 to infinity here. Alrighty. So we're pretty good in that sense. So this is our AN. So we'll say AN will be n over n to the fourth plus 1, which means we're going to look at the function x over x to the fourth plus 1. This function is positive and it is decreasing. We don't have to do any calculus. The graph is shown here. Okay. So we're going to use the integral test here. So we're going to integrate from 1 to infinity x over to x to the fourth plus 1 dx, which will be the limit as x goes to infinity t goes to infinity x over x to the fourth plus 1. So, okay. This is my I of t. This is my integral in terms of the function t. I of t will be the integral of 1 to t x over x to the fourth plus 1 dx. So what I'm going to do now here is this. This is going to be a U sub question here. Okay. We're going to integrate by U sub. So let me write this down here so you can see why I say U sub. X squared squared is x to the fourth. Your U is going to be x squared here. So we let U actually be x squared, which will mean du is 2x dx, or we're going to say dx is du over 2x. And then that integral of x over u squared plus 1 du over 2x. We're going to pull out the 1/2. Get 1 over u squared plus 1 du. We may not need that. Alrighty. 1/2 inverse tangent of u, which is really 1/2 inverse tangent u is x squared here. So we're going to replace that u with x squared, and you evaluate this from 1 to t, which is 1/2 inverse tangent of t squared minus 1/2 inverse tangent of 1 squared, which is 1. But this we know is inverse tangent of 1 is pi over 4. Okay, so I of t, let's write this in purple, I guess. I can't remember. Yeah. I of t inverse tangent t squared minus pi over 8, because you have the factor of 1/2 there. All right, now we got to take the limit here. This is an improper integral. As t goes to infinity of 1/2 inverse tangent t squared minus pi over 8. So you'll have properties of limits 1/2 inverse tangent t squared minus the limit, properties. T goes to infinity, inverse tangent t squared minus the limit, t goes to infinity of pi over 8. Now, this limit is pi over 8, because the limit of a constant is a constant. This limit is at pi over 4. Just trying to double check this, ladies and gentlemen, this so that this looks okay. We get 1/2 inverse tangent of x squared. So it's 1/2. Okay. All right. Well, let's see. Where's the what this is going to be pi over 2. That's what that is. Yeah. All right, this limit is pi over 2. So here's what we have. 1/2 times pi over 2 minus pi over 8 now. I guess we can use purple. Just double checking. And this will be pi over 4 minus pi over 8. Now, multiply the top by 2, the bottom by 2. We'll change colors, I guess. Or no, we'll keep it this way. This will be 2 pi over 8 minus pi over 8. Your final answer is pi over 8. That's a finite value. That's convergence here. So this equals pi over 8. We have convergence now for the improper integral. What that means is this series converges as well. So we'll put that less than infinity, and that means converges. All right. So, ladies and gentlemen, I got you some extra examples here of the integral test. I'm going to send it to you now. I hope you guys have enjoyed the demonstration.